Quanta image sensors are devices that sense light at the level of individual photons. These devices can run at extremely high speeds, producing binary frames that indicate whether a photon was detected at a pixel. Here, we show a tennis forehand captured at 100,000 frames per second. Sensing individual photons allows these cameras to work in extreme conditions from low light to high speeds. This capability, combined with rapid hardware advances, is making computer vision with quanta sensors an increasing reality. We're now seeing major industry adoption, with companies like Canon and Sony producing megapixel scale sensors. So, how do we use quanta image sensors for computer vision? The common approach is to first construct images by motion compensating and aggregating photon detections. Once an image is reconstructed, we can apply conventional neural networks for tasks like monocular depth estimation or point tracking. Unfortunately, this reconstruction step is computationally expensive and slow, creating a major performance bottleneck for the entire system. In this work, we propose quantum neural networks or QNNs. They operate directly on photon detections to perform a task, avoiding the costly reconstruction step. To build QNNs, we adopt existing vision models by inserting our novel QNN layers into their architecture. This makes them compatible with raw photon data, as shown here for depth estimation and point tracking tasks. We propose two kinds of QNN layers: a sensor proximal QNN layer that operates pixel-wise on photon detections, and a more general intermediate QNN layer that operates on neural network feature maps. Our sensor proximal layer is a lightweight state machine that processes individual photons as they arrive. It's based on adaptive exponential smoothing, making it fast and suitable for online processing. These smoothing weights change based on pixel motion, allowing us to aggregate more photons in slow-moving regions to reduce noise, and fewer in fast-moving regions to reduce blur. To visualize adaptive aggregation, let's compare it to just summing photons. If we sum too few, the result is noisy. If we sum too many, the result is blurry. In contrast, our adaptive layer finds a balance, using more photons for the static background and fewer for the moving car, resulting in an output that is both clean and sharp. Our intermediate QNN layer is a trainable layer that applies the same adaptive aggregation concept, but in a pointwise manner to feature maps within the network. To increase representation capacity, we use a multi-head design similar to transformers. The layer's design is closely related to modern state space models like Mamba 2, with the smoothing weights driven by multi-layer perceptrons. QNN layers allow us to convert conventional neural networks to photon-level equivalents that can run in challenging scenarios. Here we image a stress ball that is hurled at a coffee mug. We show both the photon detections and the result of summing chunks of 64 binary frames. While these sound frames make it possible to see what's going on in the scene, they are quite noisy. Running depth anything V2 on these frames results in erroneous depth inference. We could try burst denoising the frames first. This results in a better depth estimate, but this restoration first approach is quite slow, requiring over 500 gigaflops per output frame and a 6-second latency. The ball's impact only lasts 60 milliseconds, so we are far from real time. With our depth anything V2 QNN, we can infer relative depth with 6 times fewer flops and 160 times lesser latency. The significant improvement in latency is because our recurrent QNN layers avoid the reconstruction bottleneck entirely. Next, we test our method on a prize wheel spinning in low light, about 3 lux, where we detect on average less than 1/10 of a photon per pixel per frame. As before, simply summing the frames is too noisy for a standard point tracker to work. And using a sophisticated reconstruction algorithm first succeeds, but it comes with a very high cost in computation and latency. In comparison, Our QNN-based PIPS++ point tracker produces reliable point tracks in this challenging scene with significantly reduced flop count and output latency. In summary, we propose quantum neural networks that directly transform photon detections to downstream task objectives. Our QNN layers also lend themselves to efficient inference modes, such as those based on sparse eventful computations, or those based on irregular sampling instance. Please check out our paper for more details or chat with us at the poster session on Tuesday afternoon.